we'll just bring up the slides. And this is where we were the last day. Okay, this is the last thing we looked at in the tutorial, and it's really a terrible stretch to get to that. Just let me fiddle here for a second. Okay. Now, what the information here is about an instruction, and this is well beyond what it's reasonable to expect you guys to know about. So please don't take fright at this point. But I'm talking about the details of an instruction, and as I say, I realise I'm jumping the gun a bit. But what I'm saying here is that, well, let's just step back a little bit and think about what you do know about the microprocessors and so on. There's that von Neumann architecture, which I'll show you in a moment again. The von Neumann architecture, where you have the CPU, you have memory, you have peripherals, and you have a bus joining them up. Okay. Now that's a slightly more complicated model in ways of the system than you need, and we'll simplify it in a few minutes. But roughly speaking, what you've got is you've got the CPU where everything gets done, and you have memory where everything gets stored. And let's forget about the peripherals. So if you wanted to, you might remember that what we wanted to do is get the average of 10 numbers. If you want to get the average of 10 numbers and they reside in memory, well, clearly then, if you can't do anything in memory other than store information, you have to actually bring it down into the processor. You have to do whatever is necessary down there, including divide, okay, to get the average, and then store the result perhaps back up in memory. So even in that most general way, you roughly know what to do. And if I gave you the instruction set summary now, you'd scrabble around and try and make some sense of it, and you probably would make a fair fist of it. But let's go on a little bit and see, sorry, going the wrong way here by the look of it. Maybe not, hold on. Ah, yes, okay, sorry. That slide shouldn't be there. Okay, so just to refresh your memory, here's the programmer's model again of the computer system. We have the CPU, memory, the peripherals, and initially we're just going to throw most of that detail away, and we're going to end up with this. Okay? This is a simpler version. And the three components in it are all important, right? We have the 68,000 processor microprocessor here itself, and that'll be the CPU in our von Neumann machine. Okay? We'll have memory. Okay? We'll have memory over here, and memory is organized the way it's shown here. Okay? Each location in memory is numbered, starting at 0. And on the 68,000, it goes up to 16,777,215. Okay, and that, for your information, that's 2 to the power 24 minus 1. As we'll see later, we'll talk a bit more about it. And each location holds 1 byte of information. So we would say that the 68,000 is byte addressable. It's byte addressable. Okay, so you have the processor, where everything gets done. We're going to talk a good bit more about that, and I've given you a handout which we'll talk about. You have memory over there where stuff gets stored, and joining them up is the bus. And the bus is bidirectional. Okay, information can go from the processor to memory, and it can come from memory to the processor. And by the way, in our versions of the computer system, these transfers of information on the bus will always be under the control of the computer, of the processor, not of memory. Okay, so that you can think, if you want to sort of try and think of this as if these were humans in a sense, you could think that you're the processor. You're standing, as it were, in the processor, and the processor is the one that gives orders to transfer information into it or to send information away from it. Now, we can then talk about a read on the bus. Okay, so if you're standing here and you're looking for information, you're reading information from memory into the 68,000. If you're sending information for storage out in memory, you're writing it. So you read from or write to memory. They're the verbs that you could imagine using. Now, I should say, and I always forget to say this, anytime we're in virtually any computer that you can think of, whenever you read information, say from a particular location, what you'll be doing is actually reading a copy. It's non-destructive. You'll make a non-destructive read of the information that's there. At least that's how it will look. At the lowest level of the architecture of a dynamic RAM, it actually is destructive. When you read from a cell, the contents of the cell are obliterated in the process of reading it, and it has to be reconstructed. Well, that's okay. But as far as we're concerned at the level of assembly language, you're doing a non-destructive read, a copy from some particular place, whether it's a location in memory or somewhere else. It's a non-destructive read. When you write something, however, if you write a byte into location 6 there, then what will happen is whatever was there before is obliterated as if it never existed. There's no connection between what was there before and what will overwrite it. Okay? So reads and writes. Now, the other thing is the bus. The bus itself imposes a penalty on everything that you do. The bus is slow, like all buses. Sorry, hope nobody's from CLE here. But it's slow. Electrically speaking, what's happening is the 68000's electrical or electronic hardware is trying to impose signals on the wires that make up the bus, which have to propagate through the CPU, through the computer board, and maybe even further afield. They have to propagate through that to get into the memory system, which is going to take a bit of time to recognize them and use them. That's if you're sending information out. If you're taking information in, a similar thing has to happen. So transferring information on the bus is slow, and it also takes up a certain amount of energy. Although we're not going to worry about the energy side of it in this course, nevertheless you need to think about it. So if you can get away with not transferring information across the bus, so much the better. And you say, what? Well, suppose you have a piece of information that you need to do a couple of things on. You could take the information from memory, process it, store the result back in memory, take a copy from memory again, process it again, store it back in memory again, take it back to the processor again, and so on. Okay? And if you're using a primitive compiler, some of the earlier compilers, that's what would happen. Okay? You'd have a lot of transfer to and from memory. What you could do, though, if you think about it, as a good assembly language programmer or a good compiler now, will take the information the first time, and if it's possible, it will keep all the copies locally. Okay, so it'll take the information the first time, perform the first operation on it, and not send it back out to memory. It will perform the second operation on its local copy. It will perform the other operations on its local copy. Yeah, I hate that. I'm going to have to fix that. That's a real PC-ish thing. To interrupt you while you're doing something there. Your system needs to be restarted. Isn't that what it often says? You know, that's the usual answer to that. Okay, and I will get rid of that syndication agent and all that stuff later. Okay, yeah. So what you could imagine then is having a local copy of that piece of information. Now that's fine, and it works if you're thinking of one processor in your system. But in the not too distant future, you'll be working on multi-core processors, right? And it might be the case that you have the original copy up here, and you'll have a local copy which has been altered here, and somebody comes looking for it, another agency comes looking for it. Do they get the local copy, which is the most up-to-date copy, or do they get the copy that's out in memory? So there are issues that you have to deal with through a thing called typically cache coherency, right? But for the moment anyway, we just have to note that using the bus is costly and we should try to avoid it. Okay. Now, here's okay, let me just go back again. This is the 68000. You can see it's a white box, a yellow box in this case. Now we're looking inside. You want to look inside the 68000 because you need this programmer's model to enable you to figure out what to do. Okay, now think about that, getting the average of the 10 numbers idea. Well, inside the 68000, this is the arrangement that you might be able to see. Let me take you on a quick tour of it. And this comes from the 68000 programmer's manual, and it's not exactly what I would use. But anyway, there are 16 general purpose registers in it. 16, okay? And each register is 32 bits wide. And you'll remember the bit numbering that we were using from bit 0 to bit 31. Okay, 32 bits. So the 16 general purpose registers, there's 8 data registers. They're called data registers, D0 through to D7. So each one of those is capable of holding 32 bits. Okay, and then there are 8, not 7 as it says here. There are actually 8 address registers. Okay, and the 8 address registers are A0 through to A7. Now, this diagram separates A7 from the other address registers for reasons which I'll come to later in a couple of weeks' time. But for the moment, you have 8 data registers and you have 8 address registers. And their general purpose, they're for holding data of some kind. The names that they have, like data register and address register, are a little bit misleading, but I hope you'll see why they're called those in a little while. What they are for is for holding information temporarily. So let's imagine this averages business. You might, for example, say, okay, well, I'm going to take the 10 numbers down from memory, and I'm going to stick them in any registers I can find. Okay, so you might put the first one in D0 and the second one in D1 and so on. And they're for holding things. So they're a place to put something down in the processor. Now remember, these are not memory locations. These are actually in the processor. So access to them is instantaneous. If you want to get something in a data register or an address register, it's instant because you don't have to go across the bus to get it. So if you can hold something in a register, you've got very fast access to it. Instantaneous access. These registers are organized, the data registers are organized so that they can manipulate either 8 bits at a time. Okay, that's what this dotted line here means. In other words, you can treat a data register as if it's only 8 bits wide, or you can treat it as if it's 16 bits wide, or you can treat it as if it's its full 32 bits. Right? So if you have characters, and you've seen characters are 7-bit ASCII code is used for encoding characters. Typically, you'll put 7 bits in an 8-bit byte. So if you're processing characters, typically you'll be using just the byte part of these registers, right? Excuse me. So the data registers then can be treated as if they're 1 byte wide, 1 word wide, or 1 long word wide. And whenever you operate on a register as something less than 32 bits, let's say you operate on it as a byte, whatever you do to that byte, it'll have no effect on the other 24 bits. Okay? So it's as if you just chopped any operations off at this bit number 7 boundary here. Whatever you do to, say, D5 here as a byte will have no effect whatever on the rest of the contents of the register. So whatever contents they had before, they'll retain. So that's an important point to make. Some instructions, as we'll see, allow you to manipulate bits by themselves. And they typically operate on pieces of information, so-called operands, inside data registers. But we'll get to that in due course. Now, if you compare the layout that's shown here for data registers and address registers, you can see that there's a slight difference. And the difference is that with an address register, none of the instructions that the 68000 has implemented allow you to manipulate the byte part of an address register. You can only treat it as either a 16-bit wide yoke or a 32-bit wide item. Okay, so there are some differences between the data registers and the address registers as to what you can use them for. So they're not totally interchangeable. All the data registers are interchangeable with one another. All the address registers, well, A0 to A6 are interchangeable with one another, but they're not interchangeable as between, say, address registers and data registers. So sometimes when you're looking for speed, you're going to have to say, well, will I put this piece of information in an address register or a data register? Have I got room? Have I got a spare register? Will I put it in an address or a data register, depending on what I'm going to be doing with it in the future? Okay, so there are 16 general purpose registers. To begin with, just think of them as just places you can hold things. Now, underneath them, in the hardware of the machine, there's all the hardware necessary to do things like addition, because you can issue an instruction to the 68000 to take the word contents of D4, say, and add it to the word contents of A4. And so underneath, when that instruction is issued, the hardware in the processor takes the bits from these registers, performs the appropriate operations on those bits, and maybe puts a result somewhere, say back in A4 or D4, wherever you specify. Okay, so underneath this surface level, there's the hardware that gives effect to the instructions that we issue. Okay, so you'd imagine bringing information in here, processing it, and then maybe storing it back out into memory later. The other two registers here, these two registers here, are special purpose. They're not general purpose. The first one here is the PC, the program counter, not personal computer or anything like that, or politically correct, but program counter. And the second one here is called the status register. Okay. Now, what are these for? Well, okay. Now, let's see now. Okay. If you think about memory for a moment, memory is numbered, as we've just seen, and as we see a bit more of, I hope, in a couple of minutes. It's numbered. That's fine. Memory contains data, which is fine, and it also contains programs, which is fine as well. The programs are sequences of instructions, okay? And they're encoded in binary and stored in memory. Okay, now in the 68,000, instructions are at least 2 bytes long. They're always an even number of bytes, and they can be from 2 to, I think, maybe 10 bytes long. Okay, it doesn't really matter at this point, but they occupy memory. And therefore it follows that every instruction in a program must have a location in memory, the memory that it occupies. Okay? And so if you imagine a sequence of instructions, they're going to be stored in memory in sequential memory locations. Okay? Now in the von Neumann machine, when you're executing a program, you're executing it instruction by instruction. And let's say you're executing the current instruction. Okay, that's going to be in memory somewhere. Okay? And by default in the von Neumann machine, the next instruction that's going to be executed is the one that follows this instruction sequentially in memory. And that's what this program counter points to. The program counter is run by hardware underneath and is always made point to the next instruction to be executed. Okay? So if you're executing an instruction that starts at location, say 1000, and it's 4 bytes long, the next instruction, which will be in the PC, or sorry, which will be pointed to by the PC, will be at 1004. Okay, and so on. And the von Neumann machine makes this assumption that the next instruction to be executed is always the next sequential instruction in memory, and that's very handy, because otherwise you'd have to have some extra program or extra hardware to work out where the next instruction was to be found and to fetch it. And so it's a feature of the von Neumann machine that as a kind of an optimization, the next instruction is always the next sequential instruction in memory. Okay? Except when you want to change it. So suppose you have a sequence of instructions in memory, and you can imagine them laid out one after another. As memory locations increase, you have the instructions here. And program execution then would go step by step by step by step by step. Suppose you wanted to actually implement a loop, okay, a loop, and you wanted those instructions at the start to be executed again. Well, then what you'd be doing is you'd be saying, I wanted to go this, and I wanted to go back up here. You'd want to change the default way that instructions are fetched. And the way that you would do that by reference to the program counter is change it. So at a particular point, if you said, well, actually I want to branch back to location 500, you would put 500 in the program counter. And that's called a branch or a jump. And we'll see the instructions for that later. So that's what the program counter is. The program counter always points to the next instruction to be executed. Always. Supposed to. Okay. The other register here is also a special purpose register. Oh, and by the way, sorry, the program counter is logically 32 bits wide. Okay. In the 68,000, only the rightmost 24 bits are used. The upper 8 bits are not used in the 68,000 itself. Okay, but logically it's 32 bits wide, and you should treat it as a 32-bit wide object. What else is there worth saying about that just before I go on to the status register? It might be just worth saying that it's clear that the program counter is a number. Any address, any location of anything is itself a number. So, as well as being able to manipulate numbers that correspond to data, suppose you have a matrix of, intensity values in an image, that's clearly data. Those numbers correspond to data. But as well as being able to manipulate data with instructions in the 68,000, because locations are numbers, it should be possible to manipulate locations as well. And indeed it is. It's possible to calculate where a particular thing might be, to use instructions to generate a number which is the location of something you want to get. So you can have this level of indirection. You can actually figure out where something, you can use instructions to figure out where something is to be found. And we'll see that the duality there that an address, a location, is both the location of something and a number in its own right. We'll see that being used later on. Okay, so moving on to the status register then. The status register is a place where the overall condition of the computer is kept. For example, we'll see later on that the computer can be run in two modes of security. One called the user mode and the other called the supervisor mode. That information is stored in the status register, in part of the status register. We'll also see that the 68000 is capable of responding to events that occur in the outside world in what are called interrupts. And we'll see that the priority of the program that's running with respect to the priority of these incoming requests, that priority is stored in here as well. For example, you might have a low priority request coming in from outside saying I want some service, and the 68000 might be running a program at a high priority, and it will basically say I'm not going to bother with that low priority request because this is too important. So you have this priority business. That's stored in the status register. Now the two examples that I've given are long-term status or status status data about the 68000. But from instruction to instruction, certain pieces of information can be posted and stored in the rightmost half of the status register, and that's called the CCR, which stands for the condition code register. The condition code register. So, roughly speaking, this is what goes on. Instructions are being executed and results being generated and possibly being stored in registers and stored in memory. As well as that, and alongside it, typically an instruction will post a kind of a summary in the condition code register. Okay, kind of a very short summary. For example, it'll store a result. It'll indicate whether the result was 0. It'll indicate whether the result was negative, and a few other summary pieces of information like that, which is very useful for controlling the flow of program execution, among other things. Okay, so this is the programmer's model. Okay, you'll be writing a program. You have memory, you have the bus, you have the processor with its registers, you have instructions. That's the world that you have to live in when you're trying to write some code. So let's go back and let's think about our little problem. We have to calculate the average of 10 numbers? Is that right? So clearly we could, and sorry, let me just back up a little bit. And the numbers themselves are stored as words. Isn't that what I said? 2 byte wide items. I think that's what I said. Maybe I should just go back on the old slides here. Yeah. Okay. Write an assembly language program to find the integer average value of 10 unsigned word integers. Of course, I haven't said what an unsigned word integer is, but we'll gloss over that for the moment. The numbers are stored at an array starting at location 2000 in hex. So the result should be stored at 1FFE. So where is 1FFE relative to 2000? Can anybody tell me? Trivial question. It's not 8 bytes, no. Sorry, I heard it over here. 2 bytes. It's 2 bytes. 2 bytes ahead. So you have 1FFE, 1FFF, and then 2000 in hex. Okay, trust me, I know. Okay, so that's what we want to do. So looking at our programmer's model, this one, or looking at the 68000 model, what are we going to do? Anybody got any suggestions? So any kind of a guess is fine at this point. Okay, so here you are, right? Somebody has just handed you the keys to a Porsche, and you're saying, I wonder where the steering wheel is. Okay, this is our ability to write very fast, very lean code. Okay, so how do you do it? Okay, it's not a Porsche. Okay, Mazda MX-5. Anybody? What do we do? What are we going to do here? Now we've got to get these numbers averaged.
Keep the sum of them in one of the data registers.
Yeah. So if I could just change that a little bit to put the sum, to get the sum into the data registers. So can anybody suggest what we might do to cause that to happen? Basically, so what we're going to do is we're going to add the numbers together, divide by 10. So you guys are thinking of catching up something there, yeah?
Read those in first.
Say again?
Read those into memory first.
Read them into memory, yeah. Read them all into memory. Oh, sorry, no, they're in memory. Okay, let's imagine they're out there in memory. Are you saying read them into here?
Yeah,
Yeah, read them into registers. Okay. Now, you could imagine reading all the 10 numbers. I'm just doing this the awkward way. You could imagine reading all the 10 numbers, say into the 8 data registers and the first 2 address registers. You could imagine doing that. But what would happen if I said, well, actually, there's a million of them, okay, and I still want your program to work? So clearly, that approach of putting one into each register isn't going to work. So can anybody modify that a little bit?
Read the first two, then add those, and then read the third one into where you put the first one, and then add.
Yeah. Okay. So you're beginning to come up with a kind of an algorithm. Was that your idea as well?
Keep it running total.
Yeah, keep it running total. Yeah. Okay. Anybody else got any better ideas? Other ideas? Okay. Let's give it a try. To try to remember not to write on the screen. Isn't that the old blondes here? No, never mind. Okay. See, if there was a lot of blondes here, I'd have to explain the joke over and over anyway. Okay. So my suggestion, right, is that what we'll do is we know that the numbers are at location 2000, hex 2000. So what we could do is we could load the first one. And here's my first piece of code. Now, by the way, let me preface this. If you're an assembly language programmer already in the 68,000, you will realize that there's a couple of bugs in this. There's a couple of little unhappinesses in it. But they're not very significant at this learning stage. Okay, so I'm going to load the first number. And I'm going to use an instruction called move. I must give you an instruction set summary. The move instruction allows you to move information between places. Now the places could be memory locations, so you could move something from one memory location to another, or they can be registers, or they can be any combination of them. And I'm going to say I want to move a word, because it's a 2-byte quantity. I'm going to say I want to move the word that's at location 2000 into, say, data register 0. I'm assuming I have all the registers. So by the way, a little bit of syntax information. This is starting in column other than column 1. It's not case sensitive, it can be upper or lower case. However, it is space sensitive. You can't put in any spaces inside a sequence of pieces of information. Okay, there's no spaces inside that, and there are no spaces inside here. Second thing is, remember to distinguish between 0 and O, and 1 and L or I. Okay, use 0 and 1, not anything else. Right? If you want to put a comment in on a statement, you can put it in after a semicolon. Okay, an odd syntax to be sure, but it's old. It's old at this stage. Okay, so anyway, I'm moving a word from memory, location 2000, into. So this is going to cause a read of information across the bus. It's going to copy what's in location 2000. It's going to put it into D0. Okay. Now I could do this 10 times. What I'm going to do instead, though, is going to take on board some of the ideas that I got here, and I'm going to do something slightly different. I'm going to say, so here's the thing I could do. I could say, okay, I know there's a move instruction, so I'm going to move the next word. Where's the next word?
2001.
Oh, I've got 2 wrong answers so far.
002.
2002. Okay, why is it 2002 and not 2001 or 2004? Exactly. The thing is that these are words. A word is 2 bytes long. The 68,000 is byte addressable. That means the first byte of the word that's at location 2000 is indeed at location 200. The second byte of the word at location 2000 is at 2001. So it follows that the next byte is the next 3 bytes, so to speak, is at 2002. I might draw that in a minute. Okay, so we'll move this and we move it into D1. Okay, so now we have the first 2 numbers in D1. And now I'm going to use an add instruction. I'm going to simply say add, and I'm not dreaming these instructions up, although I'm pulling them out of, well, I won't say, but you might think I'm just pulling them out of the air, but I'm not. You'll see the instruction set summary that these instructions exist in the 68,000. I'm going to add the word that's in D1 to the word that's in D0. And then what's going to happen? Well, as it happens, this add instruction does the following. It takes the word part of D1 and the word part of D0, adds them together. That's the electronics of the thing, the computer logic of the thing. And then it places the result in D0. So what you could put in here by way of a comment is you could say D0 is assigned or replaced by the contents of D1 plus D0. Okay, destructive replacement of the word D0.W, because it's a word size operation here, is replaced. Right? So the upper half of D0 is unaffected by this. D1 is unaffected by it completely. This D1 here is, you might call it the source, which is often abbreviated just to SRC, and D0 is the destination, which is sometimes abbreviated to DST, the source and the destination. Okay? In the 68,000 world, if there are two pieces of information, they'll be separated by a comma but no spaces, and the first one is always going to be the source, and the second the destination. Okay. So we've got the sum of the first two numbers in D0, or have we? Okay, looks like we have. So let's move on. Okay, so we've got the first two numbers. We could now load the third number, and we could say it's at 2004, and we're going to put it into D1 again. Now here I'm reusing D1 because I'm finished with it. I know that previously I had the second number there. Now I'm going to have the third number in it, but I don't need the second number anymore, so it's okay for me to overwrite it. So I'm overwriting it here. So I'm conserving registers, as it were. And then I could say add .w D1 to D0. And so I've got the first three numbers. Okay, now, a couple of little things here. First of all, if you're lazy, and I hope you are in this particular way, you say, God, this is the same old thing over and over again, just changing this value here, 2002, 2004, the next is going to be 2006, and 2008, and 2000A, and 2000C, and 2000E, and so on. Wow, this is going to be very exciting, writing programs like this. Okay, so that is a point to bear in mind. And we'll fix that with a little more sophistication later. Second thing, though, is here is this little construct here. Now, and that one there as well. If the 68,000 was a RISC machine, a reduced instruction set computer, it isn't, by the way, but if it was, this is what you would have to do. And it works in the 68,000. Okay? You'd have to move stuff from memory down into some holding place in the processor, like a register, and then you'd have to perform the operations like add and subtract, multiply, compare, all those things. They would all have to be done, strictly speaking, on operands, as these things are called, that are inside the processor. Okay, that's if it's a RISC machine. Okay, in a RISC machine, there are many classes of them. There are a small number actually of classes of instructions. One class is for getting information to and from memory, and does nothing else in a RISC machine. And that's what we're doing here, move. And then the other class of instructions are for operating on operands that are within the processor. In a complex instruction set computer, however, sometimes instructions like common combinations of instructions are merged into one. So I'm going to use this one here. I'm going to say add .w from 2006 to D0. Okay, and that combines these two in a sense. It takes the word operand from location 2006 and 7 and adds it directly to whatever is in D0. Excuse me. So you've one instruction less to execute. And that's very nice if you're an assembly language programmer. However, if you're a hardware designer and you're designing the machine, the processor, you might say, golly, in order to actually implement this instruction in hardware, I've had to make the chip bigger, had to put in more gates, an extra stage in the delay going around the instruction execution loop. So this instruction, even when you don't use it, is going to slow the overall performance of the system down. And this is the insight that the RISC, the Reduced Instruction Set Computer crowd, had in the early 80s. They said if we remove superfluous instructions that are really only there for convenience, maybe we'll end up with a stripped down version of an instruction set that can be implemented very quickly on a small, cheap processor. And that's indeed what appeared to happen for a time. The drawback of the reduced instruction set computer approach is called program bloat. I think it's called, maybe it's not called program bloat. But anyway, you can see that whereas one complex instruction set computer instruction does it here, you need at least two here. So RISC computer programs tend to be bigger and occupy more memory space than complex instruction set computer. So the jury is very much still out on that. In fact, I think the jury has gotten tired and gone away and said, we're not interested in this anymore. Let's move on to multi-stage machines. Okay, but we could do that anyway. So let's just go on here. Add 2008 to D0. So how many have we got now? We have 1, 2, 3, 4, 5, 6. This is A. C, that's 7. 8. 20109, I hope. 10. Okay, so I think I have the 10 numbers added up in D0. Anybody see any problems with that, by the way? Because there is one. Okay, let's not worry about it for the moment. So we have the 10 numbers, now we have to divide them by 10. We have to divide them by 10. Okay, yeah, sure, I'll just put in the instruction. Here it goes, okay? Now this is wrong, okay? But let's do it anyway, sure. So I'm going to say divide unsigned. So this is another instruction in the instruction set, and that means basically it has hardware underneath to execute the instruction that you're specifying here. And I'm going to introduce a new symbol here, a hash sign, not a dollar sign, a hash sign, or a pounds weight sign if you're American. Hash sign 10 into D0. Okay, so the sense of this is that I want to divide D0 by 10. 10 numbers, add them all up.
What's that?
D-I-V-U, sorry, U for unsigned. Thanks. Divide unsigned. Now this is a divide instruction in the 68,000. If you were counting the amount of time it takes to execute these instructions, as we'll see, these add and move instructions are very fast, but divide and multiply instructions are very slow. They're of the order of 8 to 10 times slower than regular instructions. But we're going to do it anyway. We get the result in D0. It turns out, as we'll see later, that you get both the result and the remainder. You get the result and the remainder, because it's an integer division. But anyway, let's move on blithely. And we take the result that's in D0 and we'll store it out at 1FFE. Okay, so there's a bit of code. That's just to get the average of 10 numbers. Now, it's wrong. It's wrong because actually the divide instruction is a bit more complicated than I'm letting on here. So that's something we'll come to. Is there anything else though that's wrong with it? That could be wrong with it?
Overflow in the registers.
Sorry?
Overflow in the
registers. Exactly right, yes. Okay, suppose you have two 16-bit numbers, two words, two 16-bit numbers, the first two, right? The one at 2000, the one at 2000 and the one at 2002, and you add them together. What happens if you get a carry out of that? To two 16-bit numbers, you might get a 17-bit result, right? If you think about it. What happens? Well, in our case, that extra information is lost. So your Porsche is spinning off the corner, and you've just lost control of it. You're dead, okay? And what's more, it might only happen on one corner, but not on another, because depending on the data itself, you'll either get an error or you won't. And by the rule of contrariness, you know yourself, it'll happen when you're demonstrating it to somebody, or when it's, when it's controlling the descent of the space shuttle or one of those things. So you have to be very careful. That's why it's dangerous. Assembly language programming is dangerous in that sense. Not dangerous personally, well, usually. Although I heard one time that in Harland and Wolff, in order to ensure that when a ship was launched that it didn't swamp the whole bay, they used to put the engineers on the other side of the bay. Okay, so just think about that. If the ship landed down into the bay and you got a big tidal wave, the engineers got it first, right? So we don't do that kind of thing here, but you could imagine that you could be held responsible for your poor coding. So you need to be very careful. It's actually a little bit tricky to get around that problem, but it's only tricky to think about. Once you've figured out how to go about it, the actual coding of it is very simple. There's another problem, as I said, with the error use of the divide instruction. Basically, if you like, what has happened here is I haven't looked carefully enough at the actual small print in respect of the divide instruction. And the small print is this. We have treated D0, which is what we divide 10 into, we have treated it as a word everywhere, right? Because we're adding words together. Now, we already know there's a little bit of a problem with that. But notwithstanding that, we've treated it as a word everywhere. And yet, if you read the small print of the divide instruction, it expects to be dividing something into a long word. Okay, it's dividing into a long word. We've only got the word part of it. We can only speak for the word part of D0. The upper word of D0, the rest of the long word, in other words, has some kind of garbage in it. And we don't know what that is. So this program nearly, but not quite works. And it might work when you try it. But it mightn't work if you're standing on the other side of the bay, metaphorically. Okay, thanks for your attention. We'll see you tomorrow.